The notion of what a limit is critically important to study in calculus because without knowing what a function is doing at extremes, we're not able to calculate later what we call derivatives. The way that we write a limit is by putting LIM and then x approaches some value, and then we have the actual function of x. And what we want to do is see what happens to x as it approaches 0. The simplest thing, of course, is to just substitute the 0 in place of x. So at 0, the limit as x approaches 0 of x is 0. That's simple enough, but then sometimes we get a function where we can't actually put the value of what x is approaching. In this case, if x is approaching 0, then what I would have is 1 over 0, and this is undefined. And as a result, we need to look at what happens as we approach 0, but it's not actually at 0. So let's take a look at that for a second. So here what I've done is set up 4 fractions, and I'm decreasing the value of the denominator as I move on. So 1 divided by 1, well, that's just a 1. 1 divided by 0.5, that's a 2. 1 divided by 0.05, that's 20. And 1 divided by 0.005 is 200. So what happens as x approaches 0, the value of this function is going to approach infinity. And that's the solution for this one. So the limit as x approaches 0 of 1 over x is infinity. Here our limit, instead of going to 0, our limit is going to infinity. And as x gets bigger and bigger and bigger, we want to look at what happens to our function here. So if I had 1 over, and we'll do 1 squared, this would be 1. Then if I increase this, I'm getting the numbers to be bigger. Then I had 2 squared, that would be 1 over 4. And if I had a 10 squared, I'd have 1 over 100. What's happening here is as x gets bigger, heading toward infinity, the value of my function, here it's a 1, here it's 0.25, and here it's 0.01. What's happening is the value of as my denominator gets bigger because x is approaching infinity, the value of the function is dropping. And eventually this would go to 0. So the limit as x approaches infinity of 1 over x squared is simply 0. In this example here, our x is not approaching 0 or infinity. It's not an extreme. Our x is just simply approaching 3. So going off to the side, if I was to just substitute the 3, I would have 2 times 3 minus 5. Well, this equals 6 minus 5, or 1. So in this case, the simple substitution gave us the answer of 1. In this example, this one is actually not solvable by simple methods. If I was to substitute the 0 in here, what I would have is 0 over 0, which is what we call an indeterminate form. There is a way to solve this without just doing a direct substitution, and that is going to be explored in another video. I'll put a link at the end of this video, and it's called L'Hopital's rule. For this one, as x approaches 5, this function would become the square root of 5 minus 4, so the direct substitution method works here, and this would then become the square root of 1, so this limit equals 1. And sometimes you'll get something like this where it's asking the limit as x approaches infinity of 4. Well, there is no x value here, so this function would never change because it's a constant. So regardless of what x is doing, which is not part of this function, our limit would still be 4. Here we have 3 plus 1 over x cubed. As x approaches infinity, we'll go off to the side here and kind of look at this. this would become 3 plus 1 over some infinite number. And as the denominator gets infinitely big, the value of this denominator would make this fraction go to 0. So here, this entire expression would approach 3 as x approaches infinity, and this would be our answer. And just when you thought things were really simple with this, we get to a problem that looks like this. Well, with an algebra manipulation, I can change this to look like another function. And we're going to take a look at a graph of what this looks like, and we're going to see that it has an agreement with another function, and it agrees with every point, every real number other than the number 1. Because if I was to take the number 1 and put it in here, well, this is simple enough. I would get on top, I would get 0. And on the bottom, I would again get 0. So as I said before, we can use a method called L'Hopital's rule to solve this. But assuming that you're looking at this video from pre-calculus, you won't know how to use L'Hopital's rule until you get to calculus 1. In looking at this, and I substitute 1 cubed on top is 1 minus 1, which would give me a 0. And 1 minus 1 on the bottom would give me 0, so I again have an indeterminate form. But let's do some algebra to this to change what that looks like. Well, x cubed is the same as if I was to pull out, I see this denominator is x minus 1, so I'm just going to take a look at this as x minus 1 times another function. And that other function is x squared plus x plus 1. And if I had that over x minus 1 after doing the factoring, what I would get is x minus 1 divided by x minus 1 is 1. So we have one function, we'll call that f of x here, is x cubed minus 1 over x minus 1. And the other function, we'll call it g of x, is x squared plus 1x plus 1. Let's take a look at the two graphs here. Now, looking at these two graphs, this is g of x, which is x squared plus x plus 1. And of particular importance is this point right here. Since x can't equal 1 on our f of x, if I put a 1 here, I would be dividing by 0. This function is therefore not continuous at this one point. But if we otherwise see that all of the other points on the two functions are exactly the same except for this one missing point, we can then determine that their limits are also equal. And if I was to put a 1 in on the g of x, then the limit of the g of x function, if I'm putting a 1 in here, I would have 1 plus 1 plus 1. This limit would be 3. Well, since the two graphs share every other real number in common other than the 1, we can also deduce that this function's limit must also be 3. Later in calculus 1, you would never have actually factoring this. It's not wrong to do it. It's just that there's a super fast way of doing this using something called L'Hopital's rule. If you are in calculus, just looking at this as a review, I'll put a link to the video for L'Hopital's rule at the end of this one.